Hello everyone, I am Pei Zhang from Tianjin University, an IEEE Fellow. In this microcourse, I explain time domain simulation based on physics, with a focus on physics-informed DeepONet for power system dynamic analysis. Time domain simulation answers a direct engineering question. After a fault, a control action, or a renewable fluctuation, how do the rotor angle, speed, and electrical power evolve with time? For offline planning, accuracy is the main concern. For online security assessment, speed also becomes a hard requirement. The method discussed here keeps the physical structure of the swing dynamics while using a neural operator to learn the mapping from system conditions to complete trajectories. The background is a scale problem and a dynamics problem at the same time. The table compares a 1951 bus system with a 13,659 bus system. The state variables grow from about 2.7 billion to more than 28 billion. Control variables, algebraic variables, and both differential and algebraic equations also increase by roughly one order of magnitude. That means a conventional time-step simulation has to solve a very large coupled system again and again. The physical character of the grid is also changing. With high renewable penetration and many power electronic devices, fast electromagnetic behavior becomes more important, while classic electromechanical transients remain relevant for synchronous machines. Numerical integration can represent these dynamics, but the computational burden is too high when an operator needs a fast answer for online security assessment. I frame the problem as learning the dynamic solution operator, not only accelerating one scenario, but mapping many fault and operating conditions to their time responses. That distinction matters for control room use. A single accurate trajectory is useful after the fact, but online assessment needs many trajectories under different contingencies. Operators care about whether the first swing is dangerous, whether damping is adequate, and whether a corrective action must be triggered. A learn operator can answer those repeated queries much faster if the physical constraints keep the answer trustworthy. The method comparison shows why a hybrid idea is needed. Numerical methods, such as Runge-Kutta, are accurate, mature, and trusted in engineering. Their weakness is computation time. For large-scale systems, they are not suitable when decisions must be made close to real time. Purely data-driven neural networks move in the opposite direction. They can be fast and attractive for real-time assessment, but they can also generate physically infeasible trajectories. If the training data does not cover a new fault or operating point, generalization becomes fragile. Their internal logic is also difficult to interpret. Physics-informed neural networks improve interpretability by embedding physical laws into the training objective. The remaining risk is overfitting to specific training scenarios. Physics-informed DeepONet follows this direction, but the operator learning viewpoint is important. I do not train a network to imitate one curve only. I train a mapping from conditions and time to the family of dynamic responses governed by the differential equations. This is also a practical modeling choice. In a grid study, the fault location, clearing time, generator loading, and network parameters can change from case to case. Repeating a full numerical simulation for every case is costly. A pure neural model may be fast, but may lose the meaning of power balance. The physics-informed operator tries to preserve both sides, rapid inference and equations that still express rotor dynamics. DeepONet is the operator learning backbone. A standard neural network maps a vector to a vector. DeepONet maps an input function to an output function. The branch net reads the input function at sampled points. In this setting, the input represents system conditions, control variables, or parameters. The trunk net reads the output location, which here includes the time coordinate where the state is requested. The diagram on the right shows the two streams. The branch output and trunk output are multiplied and combined to produce g of u at y. The approximation inequality states that, under suitable conditions, this architecture can approximate nonlinear operators. The terms under the branch bracket encode the sampled input function u at points x1 through xm. The terms under the trunk bracket encode the query position y. The lower equations connect that theorem to dynamics. The state S of t follows ds over dt equal to f of s, u, and t with initial state s0. The solution operator g maps the input u to the state trajectory S0 plus the integral of the vector field from 0 to t for power systems. That means the network is learning the simulation result as an operator, not only predicting the next time step. The engineering benefit is that time becomes a query variable. Once the operator is trained, I can ask for the state at different times without marching through every intermediate integration step in the traditional way. The branch net represents which system and disturbance I am studying. The trunk net represents where in the trajectory I want the answer. PI-DeepONet adds the power system physics to the operator learning structure. On the left, transient stability equations are generated from fault sets, network parameters, and operating scenarios. These inputs define the system parameter set. They enter the branch net, while time-related query information enters the trunk net. The middle part is still DeepONet. Branch features and trunk features are combined to output candidate trajectories. The right part is the physical layer. The ODE block evaluates whether the predicted trajectories satisfy the generator differential equations. The boundary and initial condition block checks whether the predicted response starts from the correct operating point and respects the required constraints. The loss node combines physical loss and data loss. Data loss keeps the prediction close to reference trajectories. Physical loss prevents the network from matching data in a way that violates swing dynamics. The training loop continues until the error is below epsilon. The final output is phi star, the learned parameter set that produces a physically consistent solution operator. The diagram also shows why the method is not simply a black box regressor. The network output is immediately tested by differential equation residuals and by initial condition requirements. If a predicted curve has the right visual shape but the wrong derivative or the wrong starting point, the loss function still penalizes it. That is the bridge between machine learning speed and power system model credibility. The time domain simulation model is written as differential algebraic equations. The first differential equation is the swing equation for speed. Tj times d omega over dt equals mechanical power Pm minus electrical power Pe minus damping d times omega minus 1. If mechanical power exceeds electrical power and damping, the rotor accelerates. If electrical power dominates, the rotor decelerates. The second equation links rotor angle to speed. d delta over dt equals synchronous speed omega s times omega minus 1. When speed is above nominal, the angle advances faster. When speed is below nominal, the angle changes more slowly. The algebraic equation gives electrical power Pe as EQV over x sigma times sine delta. This expresses the coupling between internal voltage, terminal voltage, transfer reactance, and rotor angle. When delta increases, the sine term changes the electrical power transfer. That coupling is why rotor angle swings are directly connected to power exchange and transient stability. Traditional simulation iteratively solves the differential equations and algebraic equation at each time step. PI-DeepONet learns the differential system while respecting this structure. The loss is L data plus alpha times L physics. The physical part is split into beta 1 times LIC for the initial condition and beta 2 times LODES for the differential equation residuals. The loss decomposition is where the engineering constraint becomes explicit. L data measures the squared mismatch between the predicted state trajectory and the reference trajectory from numerical integration. The indices N data and P data describe how many cases and time points are included. This term teaches the network the observed behavior. LIC is the initial condition penalty. It compares predicted initial delta and omega with their true initial values at t equal to 0. This matters because transient stability is sensitive to the starting operating point. A small initial error can shift the whole swing curve and produce a misleading stability margin. LODES measures the residual of the physical equations. R1 checks the angle equation. The derivative of predicted delta should equal predicted omega minus 1 multiplied by omega s. R2 checks the speed equation. Tj times the derivative of predicted omega should balance mechanical power, electrical power, and damping. Minimizing these residuals means the neural trajectory is not merely close to sample data, it is also close to the governing physics. That is the reason the method can use less data and still preserve credible dynamic behavior. The weights in the total loss are therefore engineering knobs. If initial consistency is critical, beta 1 should carry enough influence. If derivative accuracy is the main concern, beta 2 becomes more important. The balance controls whether the learned model behaves like a data fit or like a constrained dynamic simulator. The case study uses a single machine infinite bus system, a classic benchmark for transient stability. The generator is connected through reactances to an infinite bus with fixed voltage angle. A three-phase short-circuit fault is applied at the sending end terminal, labeled node 4. This creates a severe disturbance and tests whether the model can reproduce post-fault oscillations. Because the infinite bus fixes the external reference, the main dynamic behavior is concentrated in the generator rotor angle and speed, which makes the benchmark clear and interpretable. The two curves compare numerical integration with PI-DeepONet. For rotor angle delta, the neural trajectory follows the numerical solution through the rising swing, the falling swing, and the second rise. For speed omega, the same agreement appears around both the peak and the trough. The table shows the engineering payoff. RK45 takes about 1235.53 milliseconds. PI-DeepONet takes about 75.89 milliseconds, with MAPE values around 0.55% for delta and 0.13% for omega. The acceleration is large while the error remains small. The left plot studies step size versus error. At very small time step settings, the error can be high, with the worst mark around 4.55%. As the time step size increases across the tested range, the overall average MAPE generally falls and stabilizes. The best point is near 0.41%. The interpretation is not that larger steps are always physically better. The result shows that the learned operator remains numerically stable over a broad range of sampling choices and does not collapse when the time discretization changes. The right plot studies dataset size. With only 20 samples, total MAPE is about 2.93%. With 167 samples, it drops to about 2.34%. After that, the curve stays around 2.4 to 2.6%, and the trend line slopes slightly downward. For engineering deployment, this matters because collecting high-quality dynamic simulation data is expensive. The method reaches usable accuracy without requiring a very large training set. I read these two plots together. The model is not only fast after training, it is also relatively tolerant to how the trajectory samples are prepared and how much training data is available. That tolerance reduces the burden of building a usable training library for many operating conditions. The generalization test uses fault scenarios that were not included in training. Solid curves are numerical solutions, and dashed curves are PI-DeepONet predictions. Three scenarios are shown for delta, omega, and electrical power PE. The dashed trajectories track the phase, amplitude, and turning points of the numerical curves. The match is especially important around peaks and troughs because those locations are tied to stability margins and protection decisions. The table compares RK45, PINN, and PI-DeepONet. RK45 remains the reference but costs more than 1 second per scenario. PINN is faster, around 90 to 120 milliseconds, but its MAPE values are above 46% for delta and above 54% for omega in these cases. PI-DeepONet is faster again, around 52 to 73 milliseconds, while keeping delta error near 0.5 to 0.6% and omega error near 0.1 to 0.14%. The operator structure and physics constraints are both contributing to generalization. For business and operational value, this is the central result. A fast model is useful only if it stays accurate outside the exact training cases. The unseen scenario curves and table indicate that PI-DeepONet can support contingency screening, rapid stability ranking, and early warning tasks where many possible disturbances must be evaluated quickly. The main conclusion is straightforward. Physics-informed DeepONet treats time-domain simulation as a learned solution operator, and the physical residuals keep the predicted trajectories tied to generator dynamics. In the single machine infinite bus tests, it preserves the shape of rotor angle, speed, and electrical power responses while reducing computation time substantially compared with RK45. For online security assessment, this combination is valuable. The model can deliver fast trajectory estimates while the loss design keeps the result connected to the equations that engineers trust. Thank you.